Welcome to Teaching Difficult Concepts with Electude. Today we're going to be talking about how to use Electude to teach lab scopes. So first of all, I want to show you the great lessons Electude has on utilizing oscilloscope. So we've got oscillograph, oscilloscope introduction, guided tour, step-by-step plan, using two channels, and then some oscilloscope exercises. These are great for students to go through these on their own, to either as a follow-up to your lecture or to reinforce what you're doing with students in class. But what I want to focus on today is the use of the engine simulator so you can teach students how to best utilize and set up a lab scope. The reason this is so difficult to do out in the lab is you might only have one lab scope, and if you have 10 20 students to teach, getting them each hands-on practical experience with that scope is a very difficult thing to do. So the nice thing about having access to the simulator is you can project this up on the board really nice and big. All your students can see. They can follow along and make the connections just as you're making the connections, set up the scope just as you're setting up the scope, and then you can take them through step by step and talk about how to measure an analog signal versus a digital using two channels, etc. So let's jump in here. We're gonna start here with the no fault simulator. Close the work order. Get the oscilloscope out. I like to zoom in nice and big here on the engine compartment so we can stick the pinpoint probes a little easier. We'll connect our ground and we'll turn the scope on. Now for measuring some analog signals, the auto feature is not going to work so great for a presetting. You're going to have to make some adjustments anyway. So let's start here with the mass airflow sensor. So this is a relatively slow signal, analog. Let's start this up and we'll find the best screen setting for this. So 1 volt per division, that's not so bad. We are going to lower this zero line a little bit so you can select your channel here. So we're on channel 1, the red line, and we're going to lower our zero line kind of close to the bottom here because we want to try to fill up this page the best we can. So that should be plenty of, so 1 volt per division, we should be able to fit that all on the screen. 100 milliseconds per division, you'll see that that's actually kind of too fast. Let's go ahead and change this to maybe, let's say 500. So we're going to zoom out here at about a half a second per division. And we should be able to get at least a couple snap throttles here. You can kind of see where we are here in the trace. And we can pause that on the screen. And you can talk about this with your class, about comparing patterns and things like that. But it's a very very nice way to maybe start your lecture with this pattern such as this. Now let's unfreeze the screen. If we were to make that a little bit bigger, we could probably change that to a half a volt per division, so we can we'll zoom in here a bit on that. Even better yet, get this more of a little bit more definition there. I'll add a 500 millivolts per division. So let's measure now something a little bit faster, and this would be an AC signal, but the crank sensor. You can see that's filling up the screen. So now we're going to move our zero line to about mid-screens because we got to see this is an AC signal, so we're going to move our zero line to about the middle of the screen. And because this is a quicker pattern, we need to zoom in with our voltage here. We'll just zoom in nice and tight here to start with. And you can see we still don't see the whole pattern on the screen, so we need to zoom in or zoom out. Let's change this to 1 volt per division. There we go. And you can see that what's going on here is we're seeing the sync signal, or number one cylinder, just kind of fly by randomly there on the screen. And the reason that is because we have our trigger currently set to a very at a voltage level that repeats quite often. And so this is something that students need to be real familiar with, is how to use this trigger. And so if I want to zoom in on that sync signal, I need to click on the trigger button. And we are triggering off of channel 1 because you can see it's red. You can change that from channel 1 to channel 2 up here. So let's move our trigger up. And as you can see, as long as we're in this range here, we get a nice stable pattern. Once I get down into this area, it gets kind of noisy or messy again because there's a lot going on here. So let's get up here a little bit higher. There we go. And now we're going to move our signal over here. And if I want to get one crankshaft revolution on the screen, I'm going to move this over just a little bit more. And now I'm going to change my time. We're going to zoom out so we can get one crankshaft revolution on the screen there. So if we move our if we move our sync line in line with one of these divisions, we can then easily count how many milliseconds it takes to make a complete crankshaft revolution. So you can see here it's every 10 milliseconds. So there would be 10, 20, 30, 40, 50, 60, 70. About every 75 milliseconds, the crankshaft is making one revolution. Now let's switch gears here now, and we'll leave this set to channel 1 crankshaft sensor. Now let's go over here to the cam sensor, and let's see some relationship here. The crankshaft in relation to the camshaft sensor. So for that, we're going to turn on channel 2. And we'll connect to the signal wire of the cam. And all right, let's just maybe zoom in here a little bit. There we go. And we'll pause this here. So in relation to the cam and the crank, when we see the upward slope here of the cam, the crankshaft sync is right in line with the kind of the leading edge of that camshaft signal. So if I start this back up, and maybe what we'll do this is switch gears and trigger off the cam. So let's go change our trigger. Change that to channel 2. Now of course here again we got a very random screen because my trigger is set too high, so we need to lower that voltage. So now we're triggering there off the, and we're on a negative slope. You can see we're on a downward slope, but let's change that to a positive slope. So just like a real lab scope, we can change that to positive. I don't think I got it right there. Channel slope, there we go. Change that to a positive, hit OK. There we go. Now we got a positive trigger. So here is our cam signal, and on a positive slope, here is our crank signal. So the beginning there of the cam signal, we see that aligns perfectly with the sync signal of the crankshaft position sensor. Let's zoom out here a little bit and let's get some more data here on the screen. So you can see that cam signal happens every other crankshaft revolution. So if you were to ask your students, well, how many revolutions does the camshaft make to every revolution of the crankshaft? So that'd be a good question to ask in class. So the students can study this. You could even pause this for the students Okay, so here's number one cylinder. Let's say that's the compression. So this would be number one cylinder at the exhaust stroke, and then here we got here again, and so there's your revolutions. And let's take a look at that now in relationship to fuel and spark. So let's move our channel 1 and let's look at fuel. So it looks like here's our injector pattern. Of course, we can't see it all on the screen. We can actually click auto here and we can see more of the pattern. So here's our injector. We can zoom in on that a little bit so you can see the injector pattern just a little bit better. We can, there we go. So it looks like the injector is firing on the back side here of the cam signal. All right, now let's take a look at the spark. So what we're looking at here, and of course that's barely see it, but it's happening here on the rising edge, the spark. Let's zoom in on that a little bit. There's our sync for our toggle to tell our ignition module when to open and close the primary circuit. We could probably change that voltage a little bit. One of the nice things is you can change each voltage very easily here with this. You can change each one individually. So what if we were to ask our students, based on what we're looking at here, the firing order? Can we determine the firing order of this engine using a lab scope? Okay, so so here's our cam, and we know that that's top dead center, number one on the firing stroke here. You can see where we want the spark to occur. Zoom in there just a little bit, and you can see the spark is occurring a little bit before top dead center, a little bit advanced, which is what we want to see there. And so let's check this next cylinder. Let's see if we know that the number one cylinder fires first. Let's see if this is the next cylinder that fires. So if we compare those two signals, there it's on the leading edge of the cam signal. Here it's on the backside edge of the cam signal, so it made quite a jump there. Let's check this one out and see what. Okay, that's kind of toward, so the number one was right here. Here's number 3. Let's move this over and just check number 4. That's a little further down if we compare that to here. So if we take a look at this here, we can determine our firing order. Looks like it's 1, 3, 4, and then 2. There's our firing order. So that can all be determined if, with the lab scope. Could this be used to see if maybe the timing gear or belt maybe has slipped on a car? Absolutely. You can compare this to a known good pattern to see where your spark is happening in relationship to the cam sensor, and use that as a diagnostic test to determine whether or not a timing belt or gear has slipped. Let's take maybe another closer look at maybe duty cycle. We could go into duty cycle. A good one for that is the canister purge valve. There's our canister purge valve. We're going to turn off channel 2. we'll connect this to the ground side of the canister purge. And probably most likely, yeah, and there's no canister purge going on at the moment, but we have a scan tool here. And we can control that, turn that thing off and on. We're going to go into actuator test, engine control module. And okay, let's look at canister purge solenoid. Okay. And this is a great way to explain to students the, the concept of duty cycle. So let's turn this on 10%. So there's 10% duty cycle. Of course, this pattern's a little bit quicker than what's our scope is set up for here, so we need to zoom in on this pattern. There we go. Now, why is this, you might ask your students in the class, why is this pattern not very stable? Well, looks like our trigger is set to channel 2, so we need to adjust our trigger. Now we're triggering off number 1. And remember, if we get too low here or too high, we need to be in a spot there where it's going to zero in on the screen. All right, so we can make this even a little bit bigger here. Let's change our time base just a little bit. We'll lower our channel here a little bit. I always like to make the signal as big as I can, fill up the whole screen. Okay, so there's 10%. So duty cycle is the percentage of on time. We're on the ground side of this, so we're looking at this here where the voltage is being pulled low. So if I turn this off, you can see voltage goes high, so we're just measuring open circuit voltage. And so a 10% duty cycle, we're just on 10% of the time. So that valve is just barely opening and then it's shutting. So this would allow just a little bit of canister purge. Let's go to 50%. You can see as we're varying this, you can see that the computer can do an infinite number of, not infinite, but in between 0 and 100%. So there's 50%, close to it. 50% duty cycle. So that means the off time and the on time are equal in at this point. So the valve would be approximately halfway open. Then if we go to 100% duty cycle, we'll go to 75 here first. You can see that our on time is increasing. And then if we go to 100%, that means we're dropping, the solenoid is on 100% of the time, and all that voltage is being dropped across the solenoid here. So what's being measured on the back side of that solenoid is basically 0 volts left over. If we go back to 50%, here you can see our duty cycle. So this is a great way to explain duty cycle to students and measuring duty cycle. We could do the same thing on the EGR valve. Okay. Let's talk next here about maybe measuring an auction sensor. So let's do that. Let's shift gears here. There we go. That looks like an auction sensor signal. All right, this one here, what do you think? A little bit too quick on the auction sensor signal? I think we can zoom out. This would be a slower signal. Typically, you want to see it switch about once every second. So just to kind of keep things simple, we'll put this on a 1 second per division. And we're going to lower our channel 1. We're going to lower our 0 line. And we're going to fill up most of this screen here. Perfect. So let's take a look here at the scan tool here. Go to ECM. And let's go to, let's give it some lean air and see how that affects the oxygen sensor. So when you enter actuator test, the throttle goes a little high and it makes the O2 sensor inactive. So we need to lower the throttle a little bit to bring back that oxygen sensor. So let's bring that down. Yeah, 15% looks like we got some good activity there again. All right, here's our canister purge. Respond to that. So let's see what happens here. We'll make this go lean. And definitely you can see it goes lean there. Or flat lines it. We can do the same thing with the EGR valve. Kind of test the EGR valve if it's working or not by turning it off and on. You can see if the oxygen sensor responds, what it's doing. If we go back here to actuator test, we could even make it go richer or leaner per cylinder. We could see if the oxygen sensor picks that up. We might want to zoom in actually a little bit on that. And let's see what giving it extra fuel does there. You can see that definitely changed it some, giving a little rich mixture. Let's make it go leaner. You can see how the oxygen sensor reacts to that. It's a good way to kind of test to see if your injectors are working like they should. Is to see how the oxygen sensor responds to it by just changing it by 15%. Obviously, if you don't see a change there in how the oxygen sensor initially behaves, that would indicate that maybe the injector isn't performing like it should. Let's see how it's changing. All right, we can even look at fuel trim. Let's take a look at fuel trim. We'll take a look at short-term and long-term fuel trim. All right, so we have short-term fuel trim here in red and long-term in green. If we were to unhook a fuel injector, that would take away fuel, and let's see if the oxygen sensor and fuel trim respond to that. You can see fuel trim took a jump. Can we give enough fuel to make that oxygen sensor toggle again? Doesn't look like it. Looks like we've maxed out on our short and long term, and we can't get any oxygen sensor activity, but we can see it did go very lean. Now, when we unhook the ignition coil, one would think that would make it go rich, correct? Because we would have unburned fuel in the cylinder. But what else is unburnt in the cylinder? Well, there would be oxygen in the cylinder, correct? So if we have unburned oxygen in the cylinder, this oxygen sensor cannot see fuel, it can only see air. So we should see this also, the same result, at least initially till it figures out there's a open circuit. It'll probably initially give it more fuel, as you can see, yeah, and it actually goes lean because even though there's a ton of fuel actually in the exhaust, it's going to show lean because it can't see the fuel, it can only see the oxygen.